Alright, so for this video, we're going to be looking at conditional probability. So for conditional probability to be defined, we need two sets, A and B, that are subsets of our sample space, such that the probability of B is greater than 0. Then we can define the conditional probability of A given B as, so this line between there, we say given. So A given B is probability of A and B divided by the probability of B. And so the whole point of conditional probabilities is to be able to essentially take into account new information that in some sense updates our likelihood of A occurring. Okay, so for example, suppose we had I'll take a simple example here where we have S is 1, 2, 3, 4, 5. Let's say that A is 1, 2, 3, and B is 3, 4, 5. Then the probability of A given B would be the and let's say that every single one of these elements is equiprobable. So the probability of A given B is the probability of A intersect B, or A and B sometimes we say, divided by the probability of B. So what's A and B? A and B is those elements which are common amongst the two sets. So in this case, only 3. So we'd have the probability of 3 divided by the probability of B, 3, 4, 5. And so if every single one of these was equiprobable, then you'd have this being equal to a third. Okay, so let's now take an example that actually has words and meanings and interpretations. Okay, so suppose we have a deck of 52 cards, and we want to know the probability. So probability of drawing 4 aces given we have drawn 3 aces. Okay, so essentially, we're playing a game. We have an experiment where we're going to draw 4 cards, and we want to know what is the probability of getting 4 aces given we already have seen 3 aces. Now, if there's 52 cards, it's actually a pretty easy problem. The answer is 1 over 49 because 3 aces are gone. There's 1 ace left. There's 49 cards left in the deck because 3 are gone. And so the odds of getting that last ace is 1 over 49. Easy. But we're going to go through the machinery of conditional probability just to show the example. So the first thing we do is define our sample space S, and that's going to be the set of C1, C2, C3, C4, such that Ci is a card. Okay? And how big is this set? So here I should not have put the cardinality, that's just S, and how big S is just going to be the number of ways of drawing these C1, C2, 3, 4 from the deck. And so, well, how many possibilities do you have for drawing the first card? Well, there are 52 cards. You haven't put any condition on the kinds of cards you need to draw, so you have 52 times 51 times 50 times 49, which is, you could write this as P524, which is the number of permutations when taking a group of 4 elements from a larger group of 52. without replacement. Now, this was done in another video, and you can go to that video if you need more explanation on that. So now let's define our event A. So again, we have C1, C2, C3, C4, such that Ci is an ace for I in 1, 2, 3, 4. Okay, so the condition here is that they're all aces, okay? But we haven't said what order the aces. It could be the ace of clubs first and the ace of diamonds first. And so since the way that we're doing it has an order to it, because we're drawing the cards one at a time, we can think of it as having an order. And so we're going to have to calculate the number of permutations. But this is actually quite easy, because so how many ways can you have of drawing the first ace? Well, there are 4 aces, so you have 4 choices for the first ace, and then there's 3 choices for the second ace, and 2 for the third, and then the final one, there's only 1 possibility, which is just 4 factorial, which is the number of permutations of a set of size 4. Okay, great. So that's going to be the cardinality of A. Now, what's our set B? Our set B is the elements C1, C2, C3, C4, such that Ci is an ace for I in 1, 2, 3. So without putting that condition on C4. Now, this is going to be bigger than A. In fact, A is contained in B, and that's going to be an important fact later on. Why is it obvious that A is contained in B? Is that if we choose C4 to be the remaining ace, then it's still an element of B. Anyhow, so what's the cardinality of B? Well, we have 4 choices for the first ace. We have 3 choices for the second. We have 2 choices for the third. And for the fourth card, we don't need it to be an ace. And so it can be anything. And there are 49 cards remaining. Okay? And so that's just going to be 4 factorial times 49. And so we can go back and say that our probability of A is equal to the cardinality of A divided by the cardinality of S. And the cardinality of A is 4 factorial divided by, and then here I'm just going to use that notation P52 4. And then the probability of B is going to be the cardinality of B divided by the cardinality of S. And that's just going to be 4 factorial times 49 divided by this P52 4. Okay, so now let's set up that conditional probability statement. Probability of A given B is equal to the probability of A intersect B divided by the probability of B. Okay, so that whole spiel that I went on about A being an element of B means that the intersection of A and B is actually just A, and so that's equal to the probability A divided by the probability of B. Okay, and if that's unclear, I suppose you'd have to review a little bit of basic set theory, but essentially the intersection is the set of elements which are shared amongst both sets. Okay, now since A is contained in B, that means every element in A is in B, but not all elements in B are in A. And so when you take the intersection of the two, you kind of shrink the B down to only those elements which are in A, which is A itself. Okay, so hopefully that was a good enough explanation for that. Now, okay, so we've figured out what these probabilities are. So probability of A, I'm going to cut it out there and put it down here. Okay, and then we're going to take that, and I'm going to use a different color and divide that by the probability of B. And if my Apple Pen starts to work, perfect, and here we go. Now, if we remember from high school, we know that this is 4 factorial over p 52 4, and then we can multiply by, because we're dividing two fractions, one fraction by another fraction, so we can multiply by the inverse, and we get p 52 4 up here, and divided by 4 factorial times 49, and luckily some things cancel, so we didn't actually have to figure out what the sample size of S was in this case, and so what we get is just 1 over 49, which is what we expected to get.